So, hi everybody. Thank you for coming. My name is Gabriele. Hi. Just a quick word about a few things that I do. I'm pretty involved in the Scala community and recently also a little bit in the TypeScript community. I organize, together with Marco, who should be in the room, and Ivano, a Scala conference in Italy. It's called Scala Italy. It's the logo in the middle. And I also, together with Marco, we organized the Milano Scala group. And with my company, we organized the Milano TS, the TypeScript Scala group, the TypeScript group in Milan. So if you pass by Milan, you want to give a talk on these technologies, please feel free to contact me, and we'll make sure you have a few people interested in what you want to tell us. Other things that I do, actually, to earn some money, is working in this company. It's called Buildo. I'm a co-founder of this company, and we do consulting using Scala and TypeScript. We do consulting for web applications. So I usually talk at conference about Scala, but I took this opportunity to talk a little bit about TypeScript, which is something that we started actively doing a year and a half ago at Buildo, and that we're very, very happy about. So before getting into the actual subject of the talk, I would like to define what do we mean by functional programming. This is a functional programming conference, so it should be obvious what it is. But I'm pretty sure that if we go ask around a definition for functional programming, we're going to find many. So I'm not going to give you my own definition because it wouldn't be accurate, like probably most definitions wouldn't be. But I want to set the premises of what I mean by functional programming, because you can hear a variety, a spectrum of different answers, and it's important to understand what we're talking about in the context, at least, of a single talk. So to avoid ambiguity, what I'm talking about functional programming, I generally mean programming with expressions. Some could say programming with pure functions. I prefer to think about programs in terms of expressions, because it's actually easy to map in a program what is an expression, what is not. So programming with expression is something that I'm not doing here in this example. This is a JavaScript example. It's fairly easy. So I have a list of permissions, and it's empty initially. And then I have an if-else, which is a statement in JavaScript. And I populate the list of permissions based on the if or else branches. So this may seem like perfectly OK code, depending on your background. If you come from Haskell, this is an abomination. If you come from Java, this is fine, essentially. But you are declaring a value, you're mutating it. What I make you realize is that here there is no direct connections between all these lines of code. I mean, they're fairly disconnected. The first line, the permissions line, is disconnected from the rest. It's a statement, and inside the statement, you're actually doing something actively. This is an example from Scala, where if-else is not an expression, is not a statement, is an expression, meaning that it yields a value, returns a value. So the expression is basically the same. We're returning a list of permissions in either cases, but in this case, this expression is tied together and will return a value, and the value is then assigned to permission, but it's almost as a convenience. You could directly work with the value represented by that expression, by the if-else expression. We're not actually doing anything inside this if-else. We're just telling what the value of this expression should be according to different semantics, in this case of the if-else. So programming with expressions means also that we can compose and decompose these expressions for our convenience. We can give names to these expressions. We can compose this expression into more complicated expressions. So for instance, here we have a list of users. Then we filter the users to have only the ones that subscribe to a newsletter. And then we compute the content of the newsletter for each user. And we return this value. But we could also do this. And this is the same program. We simply gave names to the expressions. And now we can take those expressions and reuse them around if we want, given the symbol that we assign to the expression, which is the name of the const here. And this is JavaScript code, of course. So the essence of programming with expression is to compose and decompose these expressions into more complicated expressions. And eventually, this expression becomes your program. The entire program is an expression. So in order to be practical to program with expressions, though, we need some requirements. You need to be able to assign this expression to some symbols for it to be practical, so you can use this symbol to refer to these expressions. I mean, you could have a giant expression with no names in it, but it would be inconvenient. And when you're using functions, it is easier to program with expressions if these functions don't actually do anything other than returning the function given the inputs that you gave them. And this is usually what is defined in terms of functional programming, right? Programming with pure functions, functions that don't do anything other than computing a value. And function expressions, so they don't really do anything, meaning that you have this program that it composes of little small pieces, and in the end of the word, you actually interpret this program and run it. And a very practical implication of being able to do these things is to have a property that you heard over and over and over in conference talks, if you are in the functional programming world, which is referential transparency, which is sometimes confusing in terms of its definitions. It's usually referred to as a way of coping with effects or side effects, but essentially has a very, very simple example that you can think of. Here you have a function that returns a promise in JavaScript, which is a computation that is running and it will eventually return a value or not, or will fail. And here you have a simple program that uses this function twice, question one and then question again. It is the same question, because maybe we want to ask the same question twice, just to be sure. So you would expect that you are able to extract the right-hand side of those expressions into a value that use that value around, right? This is composing expression, giving names. It is a practical way of programming, and it allows us to factor the common parts of our program. But this is actually a bug if you do this in this program. You're changing the semantics. And this is because, in this specific case, the promise is already running. So if you instantiate the promise and then you refer to the promise twice, you will access to the same value. You won't actually run the promise twice. You will access the memoized value of that promise. So I usually find that functional programming is defined in terms of maybe referential transparency, maybe category theory. We need to use monads in order to use functional programming, right? We need to use lazy computations. And what I realized is that all these constructs, all these constraints that we put on our code are essentially to allow ourselves to program with expressions. If you don't do this, you cannot program interpreting your program as an expression. If you don't have referential transparency, you cannot substitute symbols in that expressions. If you don't have lazy evaluation, it's probably hard to actually achieve referential transparency. So all stems out from that, and that's the reason why I like to think of this in the simplest possible way, which is programming with expression in practical terms. So, okay, but what does it have to do with frontend, right? What does it have to do specifically with front-end development? Of course, functional programming can be applied to many different areas, but in front-end development, it's pretty much a new thing. There are efforts to take this mainstream in the past few years, but it's not historically an environment where there is a strong culture of functional programming. But why is it coming up to the surface now? Because it's happening, even in functional programming. We have many languages that compile to JavaScript to try and enforce functional programming. And in order to answer that question, I would like to talk about scalability for a second. And what do I mean by scalability? Good question. If you go on the TypeScript website, they advertise themselves as JavaScript that scales. And I couldn't find an explanation of what that means. Because scaling can mean many, many things. You can scale into many dimensions. You can scale in performance. You can scale in size of your team, size of your code base. I don't know, name one. So what is that it's scaling with TypeScript, right? I try to answer this question and identify a couple of scaling issues that I think are relevant in the world of programming in general, and particularly functional programming, front-end programming. So scaling issue number one is what I nicknamed Fungal War. If you never played a real-time strategy game, you don't know what it is, but it is a fairly simple concept. This is from Age of Empire for the nostalgic ones. And Fungal War is essentially when you have a map, and then you have to explore this map. And large parts of the map are black because you haven't explored them yet, so they're in the darkness. Then you have a part of the map that is gray, meaning that you have explored it, but you don't know the details anymore, maybe because it was some time ago. You still have an idea of the terrain, of some details, but you don't have the full picture. And then you have an area, which is the white light area, centered on your character, unit, or whatever, which is under your control. You know everything about that. You know the details, you know the resources, you know whether there are enemies. So the scaling issue that we face every day in general code bases is that our light area stays the same, essentially. You can have that many things in your mind as you're working on something. The problem that you're actually working today is in the white area. The problem that you were working on yesterday, maybe it's in the gray area already, and maybe there's many colleagues of yours, many coworkers that are working on black areas that you don't know anything about. So as the code base grows larger in terms of lines of code, but also in terms of the team that is working on the code base, you have this scalability issue in which you cannot keep the whole code base in your mind. You will necessarily have dark and gray areas because the light area doesn't change, but the project does, and it grows typically. So the issue with this is that whenever you're introducing a change in your code base, you may be breaking something else, right? You, voluntarily or not, you're changing whatever else is depending on you. And having visibility over the code base is super important in order to avoid accidental changes. In a scale from realizing right now and a customer called me and told me that I introduced a mistake, you have tests, you have CI that catches errors, you have internal validation before sending it to production. So you have a variety of points in which you can realize, and it's especially important when the code bases grow large that you realize immediately whether you've introduced a change. You will have to assess the impact of your changes, whatever your changes is, introducing a new class, refactoring something, fixing a bug. So that's a first scalability issue. You don't scale with the code base. You just stay focused on your area, and your area just moves around. The second scalability issue that I can think of is complexity. And I don't mean complexity as a general word like hard. I mean complexity with a specific definition, and that is in antithesis with complicated. I mean, they're different kind of hardness. And the definition of complicated versus complex is that in a complicated system, you have something that is not simple, and that's the only thing that has in common with a complex system, but it's still knowable, and you can have many components that make this thing hard. The fact that it's hard is usually due to the fact that you have many components that are contributing to the difficulty of the problem of the system, but you can generally take that apart, study it, and work on the parts in isolation. So for example, a complicated system would be a car. So if you take a car, you can work on the tires, so you don't need to know anything about the seat belts. You can fix the engine, and you don't change the leather of the seats, right? You can work independently on the pieces of the car, and you can put them together, and you can reasonably predict how the car will behave given the changes that you worked on in isolation. Of course, you need to have some kind of integration testing of some sort. You need to know how the car will behave as a whole. But you can reasonably predict most of it just by working on a single part. And you can analyze and study the single parts. Meaning, making a car is very difficult. You need a lot of skilled people to make a car. But if you care only about a single detail, you can actually study that and work on it, and then put it back, and it will work. Oh, in approximation, of course. I mean, cars have complexities too. What do I mean by complexities? Complex systems are not simple, and again, only similarity, but they have a thing that is called dense interdependencies. What matters is the relationship between the components of this system. They're hardly fully knowable. You cannot know everything about a complex system. Even if you have perfect visibility and perfect data, you will still not be able to predict exactly how the system will behave. And it's extremely hard to take a part of a complex system and study that in isolation. So an example of complex system staying in the realm of cars is traffic. You cannot really understand traffic most of the times. I mean, I'm sure you've been in traffic, right? I mean, you're humans. And if you've been in traffic, sometimes you realize that you are expecting something to be causing the traffic, something obvious, like there's a truck sideways or there's an accident of some sort. And sometimes it's just nothing, right? You just go by, and at some point you're going, at some point you're stopping. It's hard to study traffic, even if you have perfect visibility. Even if you're looking at the traffic jam from above, even if you're looking at this picture, it's not exactly obvious to point out, looking at single cars, what's happening. You cannot take a car out of car traffic and study it and say, oh, okay, that's why there's traffic. I study all the cars, and now I know. It's a matter of relationships between the cars that makes the system complicated. And in general, complex, not complicated, of course. Language is sloppier than the actual definition. So complex problems are way trickier than complicated problems because the components behave differently if you put them in the system than when you study them independently. And at the same time, the components, when you put them in the system, they alter the behavior of the system. So you cannot really rely on studying the single parts. And you can, it's super hard to reason locally. If you remember the Fungal War metaphor where you have your own area, you need to kind of know all the map in order to work with a complex system. And in front-end development, especially in web development, we have plenty of complex systems, like the DOM. If you're working on a UI application that works with the DOM, and the DOM is where you're actually manipulating, you're brittle against pretty much everything that happens in your code base, right? You need to really know everything about your code base in order to predict, to some extent, and sometimes it's even impossible, what actually will happen. If you're working with jQuery and you have a whole UI built on jQuery plugins that directly manipulate the DOM nodes, whatever plugin you bring in can break everything, or not, which is the point. You cannot predict what will happen when you bring something in. So you need to be extremely well-behaved. And by well-behaved, it means you're crossing fingers and you're hoping that the next guy hasn't broke anything with a new plugin. So another example of complex systems is CSS, which is very familiar to web developers. You're working on your register component, and you're working on the CSS, and you've chosen a beautiful font, which is Arial. And you want that font to work. You study it in isolation. You work on the code. You commit the PR. You merge it into master. Then you try the actual thing. And this happened. Right? You have this. This is from an actual website. If you're from Scala, you recognize this font. But so this is what happened because you have an override overall somewhere else in your system that is the main CSS. And this override just trumped over all your work and changed how the system will behave. And maybe by introducing that change before this fan family Arial, you change something else that is not under the control of the other main CSS. So it is very, very easy, especially in web development, I would argue, to end up with a complex system accidentally. So how do we address these scalability issues? So for the first issue, Fungal War, this is the part of the talk in which I advocate strongly a type checker, which is sometimes a controversial point, but this, my opinion is essentially summarized on type checkers by this tweet. Type checkers, take time to read it, but type checkers essentially help you while you're developing. So summarize the tweet, right? JavaScript doesn't check anything, so you can do anything and it will run it and will crash at runtime spectacularly. And TypeScript is a bit picky, sometimes too picky. So sometimes it's an inconvenience, but most of the times it will just catch errors that you stupidly make. So what happens with type checkers is that you gain immediately visibility over your entire code base, at least for a series of things that you can reasonably predict. So it is not perfect. It is not the issue. It doesn't solve entirely the issue of visibility over your code base, but it increases visibility greatly. And if you're complaining about, but it's not a perfect solution, yes, there is a reply to that tweet, which again summarizes my feelings about this. I mean, you can still have terrible code using type checkers, but I would still advocate a type checker anyway, because it helps you a lot. And it's not a free compromise, by the way. It's a trade-off, like pretty much everything in engineering. You make a trade-off, and the trade-off that sometimes you need to fight the type checker to convince him that some valid code is actually valid. But in my experience, the amount of benefits that you get from a type checker is immense with respect to the cons, which are there. So to summarize, type checkers give you visibility. And by the way, they do not replace tests, OK? They do not replace tests. They are simply a tighter feedback loop as you're developing for catching stupid errors very quickly and for making your tests easier, by the way. I mean, sometimes in JavaScript, you test for return types of methods or functions, which is easily tested implicitly by a type checker. So if you complement tests, you complement the internal validation of tools, you can essentially use it as a pal, as a friend that will tell you, sometimes aggressively, when you made a mistake. So speaking of TypeScript, I think what they mean by scale is this kind of scaling issue. Is a code base that grows large and large and large, and you don't have an idea of what are the changes that you're introducing. Maybe because your test cases are sloppy, maybe because the code base is not written by you. There is many issues that adding a type checker solves. And this is what I think they mean by scale. Sometimes somebody from Microsoft will explain us what they mean, but I can only guess. So what about complexity, though? I mean, as I said, having a type checker doesn't grant you the magic ability of writing nice code. You can still write horrible, horrible code with a type checker. So what I would argue to solve the complexity issue is to bring in functional programming. So if you think about the definition that I gave before, functional programming is really about composing little expression into larger programs. So if you follow the, what functional programming essentially suggests, which is try to start small and try to compose things and try to be predictable in what you do. So if I give you an input, you give me an output, that's going to stay stable over time. It doesn't depend on context. You will end up with a system that goes towards the complicated direction as opposed to the complex direction. And this is due to the very nature of functional programming. So as we said, one of the main issues with complex systems is that you can put anything in the system, and this anything will fit out of the context, of the global context of the system. So if you start removing global context, and if you start imposing constraints on the expressions that you put in, on the components that you put in, then you can essentially gain a better composability of your programs and gain the fact that you don't accidentally slip into complexities. You can still do complex programs with functional programming, and again, it's not a perfect solution, but in my experience, whenever you try to follow this basic principle of non-mutating things, using immutable data structure, which all follow by the idea that we want to program using expressions, you end up with systems that are way less complex than they could be, and they're maybe complicated because you can still have many pieces. But the beautiful thing about functional programming is that if you do it properly, you can always take a thing and reason locally about the single issue that you have at the moment. So it can be a line of code. You can take a line of code and reason about that independently from the rest, because you know that moving that line of code around won't be affecting the entire program. And the line of code semantics will stay the same. So you can reason about a promise, not a promise, but a synchronous code that requires an input from the user independently of the fact that this code is named after a symbol or it's an inline function, which is not possible in the example that I showed before, for instance. So we get local reasoning with functional programming and predictability of the whole system. So in other terms, you can quote me on this, functional programming makes problems complicated as opposed to complex. And meaning that it's sort of unavoidable that we develop hard systems. We will always end up with systems that are hard and too hard for a single person to maintain and to actually make it work. But you can make the system complicated as opposed to complex so that you can manage the scale of this program. So I want to take a sip of water. In the meantime, you can watch this beautiful GIF of pasta being made. It's mesmerizing, isn't it? This is the longest part in preparing this talk, like choosing the GIF. And there are so many. Look for pasta GIF, they're amazing. So, back to Earth. Okay, that's all cool, nice. We're talking about abstract thing so far, but what do I do now? Some of you may have JavaScript code bases, right? You were like, oh, I should have done that. Yeah, nice. So should I go back and rewrite everything with PureScript, ReasonML, Elm? Well, if you have the chance of writing code in those languages, try them out. I mean, they're nice, and they're especially meant for applying these concepts. And some of these languages have a higher degree of constraints on making sure that you don't actually shoot in your foot by not using functional programming. But this is not exactly practical if you already have a code base and you want to do something. So from now on in the presentation, what I want to do is to give you the basic list of things that you can do in order to start using a type checker and start using functional programming in your code bases that already exist. So the plan to conquer the world would be this. But we made a list, okay? And now we're adding a type checker, start using FP and profit. Okay, this is an idealistic view, but I want to give you something concrete that you can take home and actually implement. So adding a type checker for a JavaScript application. Of course, this is JavaScript, so we have multiple choices. And that's like, if you're familiar with JavaScript development, this is always the case. And there will be more choices next week. But thank God type checkers are hard, so the rate of type checkers is significantly lower than the rate of UI frameworks. So if you are in the JavaScript world and you want to add types to your system without essentially rewriting things in another language, you have a couple of options. So the first and probably the least intrusive option that you have is Flow type. Flow is a project by Facebook. We tried it, a buildo. We actually experimented with it a little bit. We wrote an open source SDK for a customer using Flow. I personally spent some time documenting parts of the project because I couldn't write OCaml. So that's the only way I had to contribute to the project, which is a nice way to learn something. So we actually invested a little bit in Flow. And Flow is really nice because it has a global type inference. It has a very interesting type checker that deals well with JavaScript dynamic constructs, which is super hard, trust me. And the only problem with it seems to be serving Facebook needs in the sense that that doesn't appear to be very community-oriented. Every time we will raise a bug, sometimes it will get ignored, sometimes it would end up in some kind of internal roadmap and never fixed. It has, in general, it doesn't give a good feeling if you're using this and you're not working at Facebook, in our own experience. These may have changed as of now. This is my experience from a couple of years ago now. But we essentially dropped Flow at some point because of these reasons. I mean, we wanted something more stable, less hidden in the internal Facebook development. But yet, it's still very nice and super easy to start with. You just add an annotation, and it's an external tool. It doesn't emit code, so you can always try it and go back and just remove the types and you're done. So we landed on TypeScript, which I was very skeptical about in the beginning. TypeScript is a superset of JavaScript, so it defines itself as a language rightfully because it adds constructs to JavaScript. Recent version of TypeScript actually don't add anything at runtime that it's not in your JavaScript code. I mean, there are constructs that do this, but they're essentially being deprecated slowly, like enums or other accessors. And what TypeScript does is type checking your code and also emitting your code. So that's a little bit different than Flow. It has a code emitter, so it's able to produce JavaScript code as opposed to Flow, which is only a checker. Has a pragmatic type system, which doesn't mean much, but essentially it means that the designer of the language decided to give away, since the start, soundness. They're like, this is JavaScript, it's not ever going to be sound. And they have a local type inference as opposed to global type inference, which is Flow, which in short means that you can get information about the behavior of something that you didn't type only in the context of a single function or a single scope, as opposed to analyzing the whole program and trying to understand what is that you're doing with that function, for instance, which is what Flow does. On the upper side, it is very, very much community-oriented. It has a public roadmap, has lengthy discussions on issues. You can report the bug, and it will be at least answered to in a reasonable amount of time, and many, many times fixed. It is a very, very interesting project, and it ties nicely with VS Code, which is the editor developed by Microsoft, entirely in TypeScript. So using TypeScript and VS Code is also a very pleasant experience from the development point of view. So we decided to give TypeScript a shot. So if you want to migrate to TypeScript tomorrow, how do you do it? So my suggestion is to start small. So do not migrate to TypeScript. So do not change your JavaScript code or change it very, very little. And make your existing JavaScript code work in an environment where you have set up TypeScript. So essentially, a list of things that you need to consider when you're doing the TypeScript migration is write your JavaScript code, make it compile with TypeScript, meaning that it's not even type checked. It just passed through the TypeScript compiler and is essentially passed down to whatever else is after in your development pipeline. Then write new features using TypeScript. Now, this gives you the power of writing new files and new features using TypeScript. And in order to do that, you will eventually need to write types for existing libraries, internal components, and tools that don't have types. And you can use definition types for that. And definition types are a very nice way of gluing code. This is very common in all languages that compile to JavaScript. They have types. So you can define the types for the public interfaces of libraries, including your own libraries, as opposed to rewriting those libraries in TypeScript. So this is fundamental in the TypeScript ecosystem, as much as in the Flow ecosystem, in the ReasonML ecosystem, PureScript ecosystem, I assume. Eventually, you may want to migrate all your JavaScript sources to TypeScript, but that can take time. So you can get started by doing this progressively. So you can progressively convert things to TypeScript without stopping the development. I mean, it doesn't take much time to set up the build, and then you can leave your JavaScript files where they are and start writing new TypeScript files. So there's a couple of options that you can consider, a few scenarios. There is actually more than this. But if you're using modern JavaScript, and then you're using a transpiler like Babel to convert this modern JavaScript to something ugly, which is ES5 usually, which is a target for pretty much all browsers out there. And then you're using a bundler like Webpack. If this is your setup, you don't have anything fancy, you can just replace the transpiler with TypeScript. So TypeScript is perfectly capable of transforming your code from TypeScript modern JavaScript fancy code to horrible ES5 code. Okay? It can do that, it can minify your code, and it will allow you to have JavaScript sources, which is kind of the point at this point. It will also optionally be able to type check your JavaScript files at the best that it can. I don't recommend that. This kind of breaks all the progressive introduction of TypeScript. And those are a couple of flags in case you're going through the slides later. And don't forget about those flags, because those are very important in the world where you have to import dependencies. And there's like a bazillion ways in which you can import dependencies in JavaScript. So if you're using ES6 modules and you have a common JS dependencies, there's a bunch of complications that are really, really boring, and they're usually fixed by those flags. So they're there just as a reminder. As another option, which is what we actually use, if you use Babel as a transpiler, Babel has a subset, an ecosystem of plugins that actually change what code gets emitted in the end by the backend. So if you're using Babel and you want to keep using Babel because you have all these plugins, you can still use TypeScript in front of everything as a type checker, and then have TypeScript remove its own types. So it gives you a type-checked code, which is now clean JavaScript code. And then you go down the usual toolchain through Babel, through the plugins, and using Webpack to bundle everything. So the way to do this is essentially to say target ES next. And now you can remove one of those pesky flags because Babel handles it for you in a horrible, horrible way. There's a lot of hacks going around in order to support these things in the JavaScript ecosystem, but you don't need to know about them, hopefully. So ESNext would be the caveat here. You just take TypeScript, have it type checked, remove the types, and move forward. So you can keep your existing build, which is nice. You can keep all the ecosystem. You don't have to rewrite those. The only caveat, if you are a very, very, very eager person to try new experimental JavaScript features, TypeScript will not allow you to do that. So if you're not familiar with how JavaScript features are introduced in the language, there are essentially stages in the proposal that are for proposals, and they go from 0 to 4. So there are these 5 stages, and when they reach stage 4, it means that they will be included in the next iteration of the ECMAScript specification language. And TypeScript essentially implements everything that is from stage 3 on, so something that is likely that will end up in a language. So if you're using constructs that have been proposed and then dropped, like using the bind operator, which is this funny operator here with double colons, you will need to rewrite those code because TypeScript won't even parse it. It won't even recognize that code, although Babel will happily do it, probably. So they have different levels of choices when it comes down to implementing parsing features. So when you actually get down to writing types, you can change the extension from, you can either write new files, or you can change the extension of the file from JavaScript to TypeScript, or TSX if you're using JSX. This is a purely syntactical issue. And then you will be asked to add typings for your dependencies. So if you're using React.js, TypeScript wants to know what is that you're importing from React.js so they can actually type check your code. And you find most NPM libraries, at least the popular ones, and some non-popular ones, surprisingly, in this central repository, which is called definitely typed, which is a collection of all typings. I'm not guaranteeing their high quality. There's a bunch of any around. But essentially, you can get started by using those types, and maybe you can tweak them yourself. In order to tweak these things yourself, or if you're writing a definition file for a module that doesn't exist yet, maybe it's an internal module, you can easily do this, and it's fairly simple. I just want to show you an example of how you can type a module that is not written in TypeScript. You can just say, OK, this module exports a function, some util, and it's made like this. It essentially takes a generic parameter, A, it returns an array of A, and then TypeScript will happily check your code whenever you use the SUMUtil function inside your code. OK? So can this actually be done? What proof do you have? Well, as a case study, we used to have 50,000 lines of code JavaScript project. And it was entirely ported to TypeScript in the matter of 3 months while developing features. And by developing features, I mean we had a deadline. We had to push on features. So it's not like, yeah, we're maybe doing the login today. OK, it was actually pushing features on master directly, with a decent branching system. And we imported the internal ecosystem using definition types, which gave us the speed to quickly port these types and still keep using them from JavaScript. And then eventually, we started a process that's still ongoing of rewriting everything to TypeScript because we liked it. But this can definitely be done. I mean, this was a fairly sizable project for us, and we are not a big team. A few people, like 3 or 4 people, work on this. And they were developing features and porting things to TypeScript progressively, as I showed you before. So what about functional programming? So of course, I'm not going to talk about functional programming at length because I have 5 minutes. But I want to just give you some hints where to get started. If you're completely at zero with functional programming in your JavaScript application, there is an easy point where to start, and is stop using null and undefined in JavaScript. Okay? In general, this slide is applicable pretty much everywhere. But in general, stop using null and undefined in JavaScript because JavaScript has this weird concept for which if you don't return anything from a function, it will return undefined anyway. Undefined is a value, but it's not a function, if you get the pun. So if you stop using null and undefined, what you get is that suppose you have this kind of situation in which you have a device and a camera, a resolution, and the device may or may not have a camera and may or may not have a resolution. So a typical JavaScript API will return you undefined if these things don't exist. And a typical JavaScript developer is very optimistic and will do something like this and then explode at runtime because it's not checking anything. So if you introduce TypeScript in this thing, it would at least have you to check that you're accessing values that exist. So it will make you check the value is not null or undefined, and it will guarantee that you're not exploding at runtime in this sense. But again, TypeScript gives you the visibility over this issue, but it doesn't give you nice code. This is not nice code. You're essentially mutating things. You have a bunch of statements to check things. It is not nice, and it's not composable, and it's super hard to work with. So TypeScript is perceived as a limitation when you introduce it to a JavaScript developer, because now they have to put a bunch of ifs around to check things, which is also, I think, the same situation in Java where they introduce the optional type, and then you are forced to check for things, right? And speaking of that, you can use option in TypeScript. And if you have an API that returns option, which is a data structure that represents a value that can be there or not, then you get a nice API. Because now option, we know from extensive study of category theory that it can satisfy a monadic interface. So you can have chain, you can have map, or flat map if you come from Scala, or other languages that have flat map instead of chain, bind if you come from Haskell, or a weird symbol. And you can get, so you can rewrite your code like this, and it's much nicer because it composes. And if you remember a previous example, you can take the Lambda, and you can give it a name and reuse it somewhere else. Where does option come from, by the way? There is a library which is called FPTS that I strongly suggest. It's a library for doing functional programming in TypeScript, which defines an option type. And it works even without higher-kinded types in the language. And it uses a technique to simulate higher-kinded types, which is super interesting by itself. So if you're into reading a paper, this is a nice one that I would never understand. So I have, I think 0 minutes left. So I'm going to ignore that for a second. And I have 5 more slides. And another thing that is super controversial, but I want to throw it out there, stop using promise. even if just for the reason that promise doesn't satisfy referential transparency. So this is the same example from before. And if you use a construct that comes from FPTS, which is called task, you will get referential transparency. And you will also get a nice API that you don't need to care about anymore, whether it's asynchronous or synchronous. You just use chain and map, and it works the same. So you don't need to learn a new API every time you use a data structure that does the same thing, which is essentially structuring computations one after another. You can use this monadic computation, and it will work. So task comes from FPTS, again. It's a referentially transparent alternative to promise, meaning that it won't actually run anything until you hit the method run at the end of the word, hopefully. If you care about other aspects that are broken in promises, like runtime performances, memory leaks, all interesting subjects that are not particularly into but so I don't have much experience about that, but I can vouch for the guy behind this library, which is FunFixEffect. It's Alexandru Nedelcu, which is a maintainer of several open sources projects in Scala, and he ported most of these projects to TypeScript as well. So if you're looking for through alternative and a collection of effect library data types, you can check out FunFixEffect and the whole category of FunFix libraries from Alexandru. I have a bonus slide which I won't talk about, and I would like to thank you for listening to my talk. I have one very much last slide. If you're in the Scala community, you probably know a guy who's in the Scala community. It's called Goraz. Goraz Cosmos. He's the organizer of several amazing conferences, such as Scala Swarm, Scala B. He's a fellow functional programming lover, and he's having some difficult time, and his newborn daughter was diagnosed with a very rare illness, so she will need a kidney transplant. So if you know Goraz, and if you want to help a fellow FP lover, consider donating to this cause. And this is where we come together as a community, at least the Scala community, which he's a big part of. So just wanted to throw it out there and consider donating. Thank you.